in order to say what exactly we're doing when we perform this sequential process, we need to define some sort of an objective function to be able to say what is it that we're trying to maximize or minimize by performing the 4 steps from the previous slide. So to this end, we're going to introduce a concept, a very general concept called entropy, and we'll only discuss it in the context of active learning for this specific Bayesian linear regression problem. So let PZ be a probability, continuous probability distribution. Then by definition, its differential entropy can be written in this way. So this is a function of some distribution on a continuous random variable z. This is the differential entropy of that distribution. And so what this quantity measures intuitively is the amount of uncertainty in the distribution, so the spread of the distribution. So a larger value of the differential entropy, in a sense, corresponds to a distribution that has a smaller variance. It's a distribution where we're more confident in the region of values that z can take. Whereas when the differential entropy becomes more and more negative, then we're less uncertain about z, and in a sense we can think of this distribution as having a very large variance. So for the multivariate Gaussian, the differential entropy can be written this way. It's a function of the dimensionality of the vector w times 2 pi times e times the determinant of the covariance of the Gaussian distribution, and those terms are then passed to a natural logarithm function. Okay, so to analyze the procedure on the previous slide, let's first introduce the concept of the entropy of a distribution. So imagine that we have a continuous random variable z and a probability distribution on that variable. Then the entropy of that distribution, or we can call it the differential entropy because it's a continuous distribution, is written in this way. So intuitively, we can think of this distribution as a measure of how much the distribution is spread out. So how uncertain are we about the values that z can take? So larger values of this differential entropy correspond to more uncertain distributions. So distributions that have larger variance will have a larger differential entropy. And as the variance gets smaller and smaller, the differential entropy will become more and more negative, to the point where as the variance goes to a point estimate, so you have no uncertainty, the differential entropy goes to negative infinity. So we're going to use this measure of differential entropy for a multivariate Gaussian, in which case we can calculate that the differential entropy of a multivariate Gaussian with mean mu and covariance sigma is equal to this function, so it doesn't depend on the mean. It depends on the dimensionality of the distribution, so the dimensionality of w, and also the determinant of the posterior covariance of our distribution on w. Okay, so we can use the differential entropy to show that the active learning procedure I've described previously is a greedy algorithm whereby we are picking the covariates to measure their associated responses that give us the most information about our posterior belief of w. And in this case, information is measured by the differential entropy of our posterior distribution. And so the less uncertain we are of w, the more and more negative our differential entropy of our posterior distribution of w will be. So what we're going to quickly show is that the previous algorithm is a way of picking a point to measure that's going to minimize the posterior differential entropy among all of the options that we have. So a way to see this is to look at how the posterior covariance, which is all the differential entropy depends on, changes when we add a new measurement. So we've seen that the prior distribution for the next observation In this case, the prior distribution is the posterior distribution after observing the previous observation. So our current posterior distribution gives us a prior for what we think W is for our next observation, is equal to sigma, which has this functional form. And then after we measure the response for x naught, our posterior covariance is updated in this way, where we have our posterior inverse covariance plus this term, which only depends on our next measurement, that quantity inverted. And so an interesting thing we can see is that our posterior covariance does not actually depend on what the measurement is. So there's no y naught or no vector y in any of these calculations. So we don't actually need to know what the measurement is in order to calculate the posterior covariance. And therefore, we don't need to actually know what the measurements are in order to calculate the posterior uncertainty of the vector W. So using a rank 1 property of the determinant, it can be shown, and I'm not going to derive it on this slide, but it can be shown that the posterior differential entropy relates to the prior differential entropy in this way. The posterior differential entropy is equal to the prior differential entropy minus this term. And so notice that we've written the update to our differential entropy of the posterior as a function of the prior covariance of W. So this is the covariance calculated using all of the measurements we have up to this point. And the location or the covariate vector that we choose to measure its associated response. So from this, what we can see is that if we want to pick the vector x naught that minimizes this posterior differential entropy, we really need to pick the vector x naught that maximizes this quadratic product, because this is a constant, it's not going to change. And this term, we want to maximize this term or minimize the negative of that term. And we can do that by picking x naught that maximizes this dot product, this quadratic product. And so we see that that's exactly the rule that we had discussed previously 2 slides ago, that we pick the vector x naught for which our predictive uncertainty is the greatest, which was this value. This was our predictive uncertainty for x naught. Viewing it from the perspective of minimizing our posterior uncertainty, so trying to pick the maximum of our predictive uncertainty, viewed from the perspective of minimizing our posterior uncertainty, results in identically the same rule. So in this sense, we can see that we have a greedy algorithm because we're only picking the next point to minimize in a greedy way our objective function, where our objective is the posterior uncertainty of our distribution of W. Okay, so we discussed active learning as something that Bayes' rule and the Bayesian approach allows us to do fairly easily. Let's also look at something called model selection, which is something that Bayesian inference can also handle fairly easily. So in the context of Bayesian linear regression, when we say model selection, what we're going to mean is selecting the vector lambda. So remember that our prior distribution on W is a zero mean Gaussian, where the precision matrix, so the inverse of the covariance, is lambda times the identity, and we needed to select the parameter lambda. So this is a nuisance parameter in a sense that we have to set it, or we're going to set it, we choose to set it, but what we set it to can impact the performance significantly, potentially significantly. And so let's see how Bayes' rule can give a principled way to pick lambda using something called evidence maximization. So this is one thing that we can do to select lambda among others. For example, we've already discussed cross-validation. So this is how we can select lambda using a Bayesian approach. So we've seen from Bayes' rule that the posterior of the vector w given the data, and now I'm going to also condition on the hyperparameter lambda, is equal to the likelihood of the data times the prior, and so there we can see that the prior is dependent on lambda, divided by the evidence, which is the distribution of the data given the covariates and given the hyperparameter lambda with w integrated out. So in a sense, this evidence gives us a measure of how good our model is and how good our hyperparameter assumptions are. So let's see how we can use the evidence to select lambda. So one way that we can select lambda is to maximize the evidence. So we can pick lambda to be the argmax of the log of the marginal likelihood of the data where we've integrated out all of the unknown model variables. In this case, that's just the vector w. So in this case, we can show, I'm not going to derive it, but we can show that the distribution of y is a multivariate Gaussian with zero mean and covariance equal to sigma squared I, which is the noise, plus lambda inverse times x transpose x. So that's something that can be derived. And so now what we want to do is to pick the value of lambda that maximizes this distribution, or maximizes the log of it equivalently. So we notice that this actually kind of looks like maximum likelihood, which we've discussed previously, and in fact it is. So what we discussed previously could be called type 1 maximum likelihood, where we're maximizing the likelihood of the model over the main parameters. So this is, in this case, the vector w. By maximizing this marginal likelihood, or by doing evidence maximization, where we integrate out the main parameter, we're doing what's called type 2 maximum likelihood, which is also called empirical Bayes. And so the difference between these two is purely in their perspective. Really, it's all maximizing a likelihood over an unknown parameter. But in the first case, we maximized it over what we called the main parameter. So there was no distribution on that parameter, and we didn't think of that parameter as being a marginal where we've integrated out anything else. So that was where we maximized y given x and w over w. Now we're maximizing the evidence, which is a marginal likelihood where we've integrated out the model parameters. So for this particular problem, I won't discuss the algorithm for it. We can't do this in closed form. We would have to do some sort of a gradient method. But I'm more interested here in introducing the general technique.